on viable options for decarbonization and use of clean hydrogen. Floor is yours. Thank you very much.
Thank you so much, Johannes. Thank you so much for inviting me here. So good afternoon to you all. So I will talk about decarbonization, use of clean hydrogen. I will have quite a focus on the steel metals industries here, which will also, of course, be connected to the presentations coming after here. So I'm with Linde. We are the world's largest industrial gases company. And in this context, it's worth noting that we've been involved with hydrogen for many, many years, so roughly 100 years, actually. And particularly in the last, let's say, 3-4 decades. And today we have across the value chain, we are doing a business worth roughly 3 billion euro. So this is really important to us, and we quite continue investing into it. We have the target to invest more than 1 billion euro a year into the clean energy sector. So just talking about hydrogen there, we are working with electrolysis of different kinds. We are already operating some 150 SMRs, PSAs, so more than 80 electrolyzers. We've been involved. We have our own pipeline network of 100 kilometers. We have caverns. We have, I think, 170 ton per day liquefaction capacity, a tanker fleet of more than 1,600 tankers. We built more than 200 hydrogen refueling stations so far and counting. A lot is happening in the mobility sector as well. So we've been around with the hydrogen a lot, and we are currently dealing with about 300 projects of different kinds across the world, some in mobility, but a lot also in industry and for multi-purposes as well. In addition to that, in this context, I think it's also worth mentioning about carbon capture, because I think looking forward, we will look at a portfolio of different solutions and different technologies and combinations thereof. And we have a long track record working with carbon capture. We are cooperating in one area with BASF, in another area we are working together with Schlumberger, for example. So I come back a little bit to this. When we talk about decarbonization and hydrogen, I think it's important that also to be aware of that we should not jump to hydrogen. There are a lot of things that we should think of first, what we can do to support decarbonization, and not at least electrification. If we can use electricity, clean power directly, I think we shouldn't go to make hydrogen first, so to speak. If we can use it, of course. And also don't forget about other type of fuels, low carbon fuels that we can produce and use for this in this different type of context. So I want to emphasize that. Still, hydrogen is there. Hydrogen is highly interesting. And definitely, as I talked about already, Linde is a key player here. And we are building huge plants. For example, in the PEM sector, 24 megawatt. Kevin mentioned one of them, the one at Yara in Norway, earlier in his presentation. We have 35 megawatts electrolyzer in US in the construction phase already, and so on, so forth. If we look at the steel industry, and I think this is a good illustration also for other industries, a fundamental issue is probably not the scale up. Do we will need quite large electrolyzers? So for a scrap-based steel maker of 1 million tons, if we would take that one all the way to using only hydrogen, and in that case only as a fuel, we will need about 100 megawatt electrolyzer. And if that's a PEM electrolyzer, clearly it's bigger than the ones that we have today. And if we use also hydrogen for the reduction part, and then making direct reduced iron, and for 1 million ton, that kind of plant would require about 500 megawatt. So it's quite a substantial scale up, but I don't think that is much of the problem that we have. And I will come back to the use of the hydrogen, which I don't think is a problem. I think the problem that we need to overcome to a large extent is what you can see in the diagram to the right. It is the cost of hydrogen. And the cost of hydrogen to 60-70% is associated with the cost of the power. And unless we can get the cost of the power down, and that should be clean power, of course, then we have difficulties to have a viable situation in the steel industry and in other industries. And so that's really a key component here. If we look at technologies that we as a company and many others, of course, have used in the metallurgical and glass industries, a lot of that relates to combustion. And we have done across the metallurgical and glass industries more than 800 installations of oxy-fuel. And that's a quite interesting technology here because it relates to fuel savings, which is a key, of course, when going forward with decarbonisation. Can we use this type of technologies for combustion of hydrogen? We started a couple of years ago doing tests with different type of our burners and so on. Here is a pictures from the spring 2019, Munich, and you can see 300 kilowatt burners running there, 100% hydrogen as a fuel. It worked out quite well, I would say. And this has been particularly tested for glass melting in this case. Also at our tech center in the US, we did a similar type of test going from 100% natural gas to 100% hydrogen. We did that some 3-4 years ago, and we could see that this isn't a problem. The use of hydrogen as a fuel is not a problem. Connecting now back to low carbon fuels, if we can gasify different feedstocks of interest here, we could create a low carbon fuel. And this could be waste plastics, it could be municipal solid waste, biomass was mentioned earlier, and coke oven gas, for example. These are a little bit tricky to feed in a good way to certain processes, and we need to apply quite high temperatures sometimes. One technology here is the so-called hot oxygen technology, where we are working with 1600 degrees Celsius oxygen. So, and with that we can create, in this case, a syngas that can be used for the production of iron, either in a blast furnace or in a DR shaft. And this is something that should not be forgotten, that the production of syngas in this context. This has been tested. For example, we work together with a company called Midrex. This is a world leader when it comes to direct reduction in their test plant in Charlotte, North Carolina, and generating then a syngas with this type of technology from, in that case, from coke oven gas, but that could be any type of material. A similar type of things going on currently in Nevada, where we gasify municipal solid waste into a synchro that ultimately will be used as a sustainable aviation fuel. And using waste plastics or solid municipal waste is a very nice way of creating also, of course, a circular economy. Carbon capture is another piece in it, as I already mentioned, and using the steel industry, iron and steel industry as an example, there are multiple points where we can also capture CO2 from the main sources there. And that goes both for the dominating blast furnace-based route and for the DRI-based route using natural gas as a reductant. And we should keep in mind that transporting CO2 is way easier than transporting hydrogen. So that could be definitely a complementary solution here. And for the sake of combining the last slides I showed, we can of course have gasification and producing direct reduced iron, and also having a carbon capture of that. So there are alternatives around here as complementaries to just go directly into hydrogen steel making. And that could be similar in other industries as well. And that could also nicely connect to a circular economy. The beauty of some of this is that it's easier to fit in with the existing production structure than going directly into hydrogen. And of course, we can phase in the use of hydrogen into these processes very nicely. However, if we look at the first steps, many times it's not about the reduction, it's about it's about using hydrogen as a fuel. And to do that in an efficient way, we should of course be as energy efficient in our processes as possible to minimize the use of hydrogen. And typically, as we've been working with, is go from air fuel combustion to oxy-fuel combustion, which would then reduce the need for fuel by 20, 30, 40%. And of course, we will have the corresponding CO2 savings. So that's a way to minimize the requirement for hydrogen in that situation. So we would say that the path is going from air fuel combustion over to oxy-fuel combustion, and then from with natural gas, for example, and then start using hydrogen there. This has been testing in full scale, and one great example is the steel producer Ovako, based in Sweden, where we 2.5 years ago did the first full-scale test. We have done other full-scale tests together with other customers over time. And that has been done for heating of steel. So we have done tests with, in this case, 25 tons of ball bearing steel grades. We have done tests with stainless steel up to 50 ton, etc. and so on. And the good thing here, the good news is that this company, Ovako, is now taking this into full-scale permanent installation that is supposed to be commissioned in May next year, using 100% hydrogen for heating the steel in 24 of those pit furnaces that you see in the picture. I see this as a very good example, taking this into reality. Another area is to heat ladles in the steel or iron or also non-ferrous industries, and using the flameless oxy-fuel and combine it with hydrogen. I think this we will see coming now in next year in full scale. So looking across the steelmaking processes, I have here sketched the production routes and circled the processes where we see potential use for hydrogen, and I also added comments on where we are currently. And as you know, in the DRI, famous hybrid projects and others, the pilot scale testing is going on. We had tests in full scale with use of hydrogen in blast furnaces. But as I just mentioned, we also see it for reheating. We have the first scale commissioning next year also for ladle preheaters. We see it used for cutting. We see it used for burners in electric arc furnaces. I know that Nico and others will come back to this later. So we are quite well underway with this. What I'm seeing in the steel industry, at least, is that the use of hydrogen as a fuel is going ahead quite well, and then the big scale use for reductant is coming in more in the next step, I would say. And summarizing this a little bit into some near term, mid term, long term, I think we see the increased energy efficiency and the start of the use of hydrogen as a fuel as what is happening in this type of industries across the next year, which also fits very well with the ramp up of the size of electrolyzers, the availability of renewable power and clean power for that. And then the bigger scale will then come a little bit later, including the use as a reductant. So we're sketching the future, for example, for a steel plant that would then require like a gigawatt electrolysis, and that would probably be 10 years from now or something like that, where you can use hydrogen for all different processes, and it will take a bit of time, of course. And as a last example, tying back to previous presentations, we have, of course, the hydrogen value chain related to production of green ammonia. And what, of course, there's a lot to say about this, and I will leave that out. But the thing is that this, in the same fashion as with ammonia, we have the same with steel, that we can create different hubs where we cater to different needs. We have different off-takers, and we have a big one. It could be the ammonia production, it could be the steel plant and so, but then we are also catering to other needs in the mobility sector, etc. So those are some examples I wanted to share with you. I would say in general, I don't see that we will have a large problem with scaling up the supply of hydrogen on site. Hydrogen is difficult to transport, but scaling up supply on site, I think we will go quite well. I don't see much of difficulties to solve the use of hydrogen for typically metallurgical and other industries. I think the biggest challenge, particularly in Europe, is the supply of renewable clean power to cater to these needs. And that includes, of course, expansion of grid and so on. So this was my little overview for you. Thank you very much indeed.
Thank you, Joachim, for your insights on what is really going on the industrial scale. I think that was very inspiring and very dense in terms of information. You have your contact details provided here, so that we will go to the next speaker in terms of keeping the time, which will be Thorsten Haug. He is working for the VDI Betriebsforschungsinstitut on process optimization, iron and steel making. And as we have been already now by the talk of Joachim quite deep into steel processes, we will also hear from Thorsten on decarbonization scenarios for the European steel industry. Thank you for your presentation.
So, hello, I hope you can hear me and can see the presentation.
Yes, perfect. Thank you.
So, thanks for the nice introduction. And I think definitely we have a good red line and it's quite consistent what we're presenting, comparing to what Andreas started and also Joachim further showed. So, I'll start with a short introduction, then give some overview about the project Green Steel, which is the main source of information which I will discuss today. And that is namely some decarbonization scenarios which were developed within this project for the steel industry in Europe. And finally, leave some comments regarding industrial symbiosis and its importance for the decarbonization of the steel industry. So BFI is a daughter of VDH, the Association of the German Steel Industry, but also a European steel industry. We're a non-profit institute and doing applied research. So most of our work is directly implemented in industry with a lot of industrial partners, but also a lot of research partners, which you can see all over Europe mainly. And yeah, we have 4 strategic fields. The first, of course, decarbonization, energy efficiency, most important currently, but also digitalization, industry 4.0, circular economy, and process innovation and process optimization are important topics. So the project Green Steel for Europe, it was finished in autumn last year. It was a rather large consortium with all main research institutes of the steel industry. And it was had the main objectives to plan the technological transformation of the steel industry, to identify barriers for the decarbonization, to have a direct communication to the stakeholders, and also to rate the investment demands and funding mechanisms in Europe, but also national programs. And finally, to evaluate and recommend policy options. So we had basically 3 work packages. First one was the technology road mapping, which mainly resulted in the figures I will show you. And then another work package looking to the financial aspects and the political aspects. So we had mainly 4 topics which we started. First, we collected the technologies which are available and rated them with some road mapping, looking to the development of the technical maturity, for instance, so on. Then we look to the decarbonization barriers. So why are these technologies not already installed? And we had a quite close discussion with the stakeholders, so the steel industry producers, to get a direct feeling, also verification of those barriers. And finally, the main results, these decarbonization pathways, which show some reliable estimations of the overall situation of the European steel industry in 2030 and 2050. So here you can see a quick view of the most important technologies we've selected. The most important ones finally are the lower ones here. So the direct reduction, which was already discussed, but also plasma smelting and electrolysis on the later stages will be important. Also scrap usage, for instance. So it's just a selection of different technologies with also different maturity stages. So we analyzed all of these technologies. As example here, the direct reduction route, which was already discussed. We selected important framework conditions for this technology and also discussed possible barriers. So you can also see here availability of renewable energy, which was just mentioned by Joachim. And furthermore, we did the road mapping with an estimation of the maturity development, also looking at the costs which are assigned to the different stages of development, and also give some estimation of the industrial development in real industrial production. So this was done for all the stages. And then we had this discussion of possible decarbonization barriers, first developed by desk research and then in detail discussed and assessed by industrial companies. And the results were that mainly the financial barriers, as already discussed or mentioned by Andrea, mainly the financial barriers are the issue. So most of these aspects are financial barriers or related to financial aspects. So, and then the last important step was to get a view about the possible future situation with regard to the technology development and the industrial production of steel. And we developed future scenarios for this and first looked at the barriers, but main important point also to look at different national boundary conditions. You know, the different states in Europe have different boundary conditions. So the northern European countries were already mentioned with a large part of renewable electricity, but also availability of CCS, of natural gases and so on is different in the different countries. And finally, we had detailed discussion with the steel industry and also used our expert knowledge of the different sites. So here you can see the sites with their production. And we knew about the plans of these sites so far as already known. And we tried to fuse all those information into these scenarios. So this is the basic scenarios. It's also called mixed implementation, naming I've already seen in Andreas' presentation. So in 2030, we assume that still the main part of the production of the steel is done by blast furnace, by the blast furnace route, but with different stages of optimization. So we assume that all of them will have improvements in CO2 mitigation measures, but the main part of mitigation is done by the direct reduction route, which was already also mentioned. And you can see what was also consistent to was mentioned, the main part, the large importance of natural gas. So important for this decision towards the direct reduction route is the flexibility that you can run it either with hydrogen or with natural gas or with mixes of both. So from this basic scenario, we will we would reach the targets which were at that time the right ones, but now they've increased the mitigation degree, so it's not sufficient anymore. We need to get further to select some of the other scenarios which assume, for instance, increased H2 availability, but also a worst case scenario for delayed implementation. So I cannot present all those scenarios, but I will go to the conclusions. So the energy crisis, which came up after the final report of the project, definitely changed the situation. So the natural gas availability and their cost, it's important aspect in the transformation state. So the Russian attack on Ukraine hit the European energy supply to the bones. So it was a problem not just with the, let's say, financial capacity of the steel industry, but also the overall economic viability of all technologies, in particular of this intermediate step of direct reduction based on natural gas. So the effects may be that the investments may be delayed before 2030. That's not completely clear yet, but it seems like this. But finally, the profitability, at least compared to the usual fossil way of production, may benefit after 2030 due to a larger or sooner ramp up of the hydrogen and renewable energy supply. So the roadmaps have to be adapted to new boundary conditions and new view. Also, in some places until that time, some technology ideas came up. However, it's all not casted in stone. So aspects of industrial symbiosis. The main important is the supply with renewable energy. So CO2 footprint is important. The fluctuation of the availability and the costs is quite important for the operational costs. And these operational costs are definitely defining the existence of the steel industry in Europe. Furthermore, same for hydrogen, looking also at possible different alternatives regarding the H2 derivatives, but also the question local production or import of energy is important. And finally, the alternative of fast decarbonization with a rather low percentage or full optimization, which may take some more time, is an important question. And all this depends on the energy systems and also on the integration in particular of the energy systems. But because this defines the availability, the fluctuations, and all the costs and their fluctuations. So this is quite important. And also at the same time, the change of technologies from blast furnace to direct reduction, other technologies needs a complete adaptation of the material and energy flows and also across industries. So this is the question for this is, do we have a fixed political definition of targets, or will we have a free techno-economical development of for these transformations? So it's to some extent still an open question, and also something which may be important, that the high energy cost will change the return of invest for many energy and heat usage optimization. So a lot of technologies exist, but are not implemented yet. So the conclusions are the steel industry transformation will result probably in a heterogeneous situation, at least in the next 15 years, because different plants will have a different speed of transformation. And the H2-based direct reduction electrification will play major roles so far, that is clear. However, the boundary conditions are changing, and so are the decarbonization roadmaps, in particular because the hard global market settings that forces the steel industry to have a look at the costs, because otherwise the existence is definitely in danger. And very important for this, existential important, is the integration of the energy systems, because this defines the supply, the availability, and the costs and their fluctuations. So the final conclusion is the industrial symbiosis has an existential importance for the decarbonization of the steel industry, and it needs a continuous and holistic coordination and optimization. So thanks for your interest, and I'm interested if you got some questions.
Thank you, Torsten. A special thanks from my side or from the whole project, also addressing this industrial symbiosis options and activities that you nicely addressed in your talk. And I think that is a really big fruit for thought for us in the project team. Is there any question? Probably one question. time for one question. If this is not the case, I would thank you very much also again for your elaborations. And I will hand over the word to Antonello Di Donato. So we are going to Italy now, and he will talk about knowledge and technology cross-fertilization in the steel decarbonization sector with a focus on industrial symbiosis. Thank you. The word is yours.
Thank you. Thank you. Good afternoon to everybody. I think that you can see my screen. Okay.
Yes.
So, I am Antonello Di Donato. I work at Rina Consulting Centro Sviluppo Materiali, CSM, and I work on steel processes. So this presentation is a presentation focused on a possible industrial symbiosis related to the steel processes, steel plants. And the focus of the presentation is on the fact that to be developed, to be acceptable, to be competitive and accepted, industrial symbiosis should guarantee productivity, quality, and costs. So this needs adapting and improving technologies. So there is a species of mix of technologies from different sectors to play together to develop new technologies, new industrial symbiosis. I present some examples derived from the experience of the typical steel plants in Italy, which is mainly based on electric arc furnace, which is a system to melt scraps. And the Italian steelworks based on EAF are strongly embedded in the territory. So it's really necessary an exchange of materials and energy between the steelworks and territory, which is a trend in development. The first example refers to the use of alternative fuels into electric arc furnace. Electric arc furnace is mainly an electrical machine, but also fossil fuels are used, for instance, natural gas and coal. These fuels could be replaced with non-renewable plastics, but plastics that cannot be recycled, or biomass. This could replace fossil fuels, and this can be alternative materials. This needs to develop new technology solutions for production, preparation, treatments of these materials in order to be used. For example, the first example related to the use of the plastics, plastic that cannot be recycled in the plastic industry. And in the project PolyInspire, the plastics have been used, and the aim and pre-treated in order to have easy injection, to be handled, to be used without problems in injecting the plastics inside the furnace, and at the same time to have similar performance of the process as in the case of fossil fuels. And in particular, to control the form of the slag, which is the typical practice to improve the performance of the melting process. For this purpose, plastics, which are of course a mix of different types of materials with different shapes, different characteristics, different density, and so on, has been treated in order to produce a consistent material, which is always in the same form, in the same density, in the same grain size. So these techniques derived from the typical techniques used in plastic industry for extrusion, lamination of plastics, has been adapted to develop a specific material for injecting into the electric arc furnace. On the left, there is the original plastic materials, the wastes, let's say. On the right, there is the new product developed with this new technology for plastic treatments. Besides, the project developed special injectors in order to inject these materials inside the furnace in an easy way, in a controlled way. The aim, the final technical aim was to reproduce the behavior of the coal, which is injected in such a way to be dissolved in the steel and react with the slag. So there was a big effort to reproduce the behavior with a very different materials, plastics instead of coal. The effect was good. The process was successful because, and this is proved by the same behavior of the process when using coal, fossil coal, and the plastics instead. In these graphs are reported the typical amount of charged materials in the two cases, the reference cases with coal and the cases replacing 50% of the coal with plastics, and the behavior in terms of active power. A second example refers to the use of biomass. In this case, biomass are available, but there are many problems linked to the logistics, cost, collection. But from a technological point of view, the main problems and the problem faced in this project, GreenAF and GreenAF2, was to develop a special biochar from biomass, which can be injected with the same difficulties and the same problems as in the previous example with plastics. Exploiting the fact that the pyrolysis of the biomass can be carried out in different conditions in order to have more char or more gas, and with different characteristics, different types of biochar have been developed. One specific for injection as powder through special injectors used instead of the injection of powder coal, and several types, to be charged together with scrap from the basket used to charge scrap into the furnace. And this special technology now can be considered consolidated technology, is well established and regularly used. The problem is the supply of the biomass. On the other side, the EAF can supply energy. The EAF, the electrical arc furnace, has a lot of thermal wastes, that are not used, extinct, especially with the top gas, the process gas. This thermal energy can be recovered with special technologies for recovering thermal energy at a relatively medium temperature, around 600, 700 degrees, and can be used to supply electrical energy or thermal energy, depending on the season. For example, in summer, electrical energy, in winter, thermal energy, and this energy is supplied to the territory. So from the territory arrives wastes, plastics, biomass, residues in general, and the electrical arc furnace supply energy to the area. So there is a real symbiosis between different actors in the zone. The last example is the valorization of the slag. The slag is a residue of the electrical arc furnace, which is used for some specific applications, but is not easy to be used, to be valorized. And in this case, the real problem, the real objective of, for example, this project, which is a national project, is to produce an added value materials. And as a first example, the dry granulation of the slag, which is in a technology enough solid for blast furnace slag, but not so used, not so developed for electrical furnace slag. The dry granulation can produce materials that could be used for more application inside the steelworks or in external environment. For example, for the scaling or other activities. And this is an example of the dry granulation of the slag. Finally, as a last thing, it can be possible to use atomized slag, which means to produce very small particles to be used in possible 3D printers for printing ceramic components. In this example, we have performed atomization of a slag, producing amorphous slag particles very fine, around 50-10 micrometers, with a typical vacuum induction gas atomizer for producing metallic powders. In this case, we have adapted the technology to produce slag powders, and these slag powders could be used, there are experiments in progress, to produce special components for the steelwork itself, or also for other contexts. For example, special materials for refractory materials for the steel processes, or construction that could be civil construction or industrial construction. So these are examples to show that industrial symbiosis can be declined in different ways and can be useful for global saving of material and energy, favoring in this way the decarbonization. This example aims to demonstrate that together with the legislation, rules, infrastructure, a need to develop and to install at the industrial level industrial symbiosis is to develop new technologies. And in many cases, these new technologies can be developed using existing technology with appropriate improvement, appropriate adaptation, with an exchange of knowledge between different sectors, an exchange of technologies in a species of technological, industrial symbiosis. Thank you.
Thank you, Antonello. That was really very inspiring. All the various options that you showcased in terms of how to perfectly embed an electric arc furnace in the overall industrial environment, and then showing us how probably industrial symbiosis can work in that field. We have a bit of time for 1 or 2 questions. Are there some for Antonello from the other speakers or audience? Is there any question coming up?
You can write me for some questions in the future.
Okay, perfect. Perfect. Thank you again for that talk, Antonello.
It
Great.
was a pleasure.
Thank you. It was a pleasure for us. With that, I would like to hand over to Nico Schmitz. He's working for RWTH Aachen University in the Industrial Furnace Technology Development Department or field. And now we are coming from the two alternative fuels from the more or less production side and also insights into R&D there towards really the application in a furnace probably and what is related to that. Thank you, Nico, for your talk.
Yes, Johannes. Thank you for your kind introduction. So now we go into not a deep, but a small dive into the downstream steel processing and how to decarbonize it. And we will focus today on hydrogen and ammonia, as the workshop is more about that. And electricity will be only a small part of that. So first of all, let's have a look at the production flow for flat and long steel products. And we'll start with the upstream part, which is not the main focus today. So starting with iron making, scrap melting, and then the steel making, the basic oxygen furnace shop, going over continuous casting and then to the downstream part here. And the same is for the scrap melting in the EAF electric arc furnace route, which also will go for casting, more in the long product direction, not only long products, but more than that, then also going into the hot forming. And then we are on the downstream part. So what we will look on today is not the upstream part, but more the downstream applications. And here you can see the main processes we have there, and we will look on today. So for hot forming of metals, especially for the steels here, we will have a reheating step or intermediate and post-heating. And this is the case for flat and for long products. And especially for the flat products, we will have additional annealing process after the cold rolling. And there we have a continuous process, which is called continuous annealing or galvanizing, if we do the additional galvanizing step here, or a batch annealing step, which is performed in batch furnaces. For long products, a subsequent heat treatment is not typical, but it can also be the case. But we want to keep it simple today, not to go into a deep dive, so we look at those three main processes here. Starting with the reheating furnaces, and this is nearly the same for flat or long products. We have big reheating furnaces, which are there to reheat the steel slabs and bars after continuous casting. So on the left side on the picture, you can see such a furnace, quite big furnaces, up to 50 or 60 meters long, really big productivities of up to 450 tons per hour in continuous operation. And they do heat the product from room temperature or 400 or 600 centigrade up to 1250 centigrade typically. They are equipped with quite big heating powers between 30 and 250 megawatts. You can see so really big furnaces here, really big powers. The heat is generated by direct combustion. So we have burners in the side walls and also in the top of the furnace and in the roof. And we normally do air combustion here, but oxy-fuel is also an option, for example, for better energy efficiency, and also maybe an option for hydrogen oxy-fuel and decarbonization. Typical fuels today are natural gas and steel plant gases, so coke oven gas and also mixes. If we now look at decarbonization options, we are more or less the option to electrify this. And you see the yellow arrow here on the left side. We have some challenges concerning the power density and the high process temperatures here. So one option would be resistance heating, but with those high power densities here, if we want to retrofit those furnaces, that will not work. So for retrofit installations and reheating, we have quite a lower TRL at the moment, especially for flat products. If you go for greenfield applications for long products, there are viable solutions with pure electrical heating. But if we look at those retrofits, we are going more into the direction of sustainable fuels. There, the challenges are obvious, the availability and the transport, and there may also be issues with NOx emissions. I will explain it later. Generally, the TRL is higher, but demonstrations of the full processes are pending. If we now go downstream, more downstream for the heat treatment of flat steel, we have the continuous annealing or galvanizing lines. The process taking place there is a heat treatment, so defined heating and defined cooling of the product in continuous operation. So you see the productivity is a bit smaller there, 50 to 110 tons per hour, with a heating capacity of 15 to 30 megawatts. And the process temperatures are also lower, between 750 and 1000. 1000 is also an exception, but we are more between 750 and 850 here. Typical heating principle here is also combustion, but indirect. So we have radiant heating tubes inserted in the furnace to divide the combustion products from the product. And the product is surrounded with a protective gas atmosphere here. The typical fuels we use are also natural gas and steel plant gases. And if we look for the decarbonization side, we have a clear option to decarbonize those furnaces by electrification. Typical topics and challenges here is the electrical supply, because you will have more than one continuous annealing line in an integrated steel mill. So you need 30 or 60 megawatts of additional electricity power there. And there's not so much long-term experience with electrical heated furnaces. To sum up, it's a higher TRL here, and also first lines are in commissioning. So we have those big H2 Green Steel project in Sweden, for example, and they are building a full fossil-free electrical heated galvanizing line, for example. If we look on the combustion side, we have the same issues that we had before, so availability and NOx emissions. But here we have running projects that demonstrate the utilization of hydrogen, for example, in radiant tube heating at our department. And demonstrations here are also pending. We are working on that topic. If we go for batch reheating, batch annealing furnaces, it's also for flat or long products. We have smaller furnaces, but a lot of these. So the process is also heat treatment of steel strip, and it's batch operation, so 1.0 to 2.5 tons per hour. And you see the furnaces with 0.6 to 1.8 megawatts are a bit lower in capacity, in heating capacity. But anyway, you will have 40 or 60 bases of these furnaces next to each other. As you can see on the picture, here are several furnaces placed next to each other. And they also typically worked with combustion and indirect combustion, because we want to protect the coils or, for example, the wire rod from the combustion gases and insert protective gas atmospheres. For decarbonization options here, electrical supply is the only challenge we have, because we have a high TRL, we have furnaces that are electrical heated in operation already. For the combustion with sustainable fuels, especially talking for hydrogen, there are some demos that will go into operation next year. So we will see full hydrogen combustion in bell annealing furnaces next year. For example, I think it's done by Tinova LOI, but you can see there's much movement at the moment in the downstream processes. If we now look at the fuels we have as options, it's hydrogen and ammonia. And if you look at the fuel properties here, I've marked the most important ones for us, for the combustion technologists. The one is the adiabatic flame temperature. If we compare methane, so basically natural gas, or propane, with the hydrogen combustion, we have a higher flame temperatures, which could lead to issues with thermal NO formation. Additionally, we have a real high burning velocity, which is kind of a measure for reactivity of a fuel, and it's nearly 10 times higher than the methane. If we now look at ammonia, it's quite the opposite. So the adiabatic flame temperatures are lower, could be an issue for high temperature processes because we need to generate high temperatures to have heat transfer to the product. And the second point is the low laminar burning velocity here, so low reactivity. This could be a possible issue to allow complete combustion because the combustion kinetics are slower then. I want to give some words about NOx emissions here, because for our plants, it's not typically that we have DeNOx systems. Normally, we only work with primary measures to lower our and to minimize our NOx emissions. And for hydrogen systems, the higher thermal NO formation is the first issue. So you see down there in the blue color here, this path of NO formation, it's mainly attack of radicals, so oxygen radicals or hydrogen radicals that attack the molecular nitrogen and lead to NO formation here. And this is mainly dependent on the residence time of the gases at high temperatures. And thermal NO formation can basically be tackled by us by advanced combustion technology, so primary measures. So we adjust our burners, we adjust our processes, we insert, for example, implement flameless combustion here to lower the peak flame temperatures, to lower the NO formation. The second point is about ammonia. So ammonia is one species which is basically fuel NO formations. So you see it's quite more complicated here. We have several steps that can happen. And basically the most important take here is that if we want to combust ammonia to nitrogen and water, we need nitrous oxide for that. So we need NOx to oxidize this ammonia. So it may be not possible to have a low NOx combustion by only doing primary measures. And this could mean for us that we have in our furnaces to implement secondary measures, so DeNOx plants. This is not typically for us. An alternative that could be viable for us for direct instead of direct ammonia combustion is ammonia cracking, and we heard something about that before. And so one option is we crack the ammonia to a forming gas, so H2N2 mixture, and directly combust this mixture without any purification or so on, because we do not need high purified gases, and this could be one option to save some energy here. Another option would be the purification, for example, with PSA and then combustion of the pure H2. We have to keep in mind that we have an additional energy demand here to crack the ammonia. So we need a temperature of about 750 to 1000 centigrade and a catalyst to crack the ammonia. But in our plants, we mostly have high temperature waste heat. So maybe it could be an option to create some symbiosis here and put the ammonia cracker in the off-gas system of the high temperature process to have the ammonia cracked partially or completely to combust it in the furnaces, because we have really good waste heat potential in most of the furnaces. One potential issue could be that traces of ammonia in the forming gas, for example, if you do not do any purification, might lead to higher fuel NO emissions, like I explained before. But this could maybe also a combustion technology research topic, or we have to implement secondary measures here, so a DeNOx plant. So to sum up a bit and to formulate some research needs and questions, to give a short outlook. So general, the application of H2 and ammonia in downstream steel processing is generally possible. It's all about availability, price, and the specific location we look at. So the hydrogen has to be there where we need it, and this will possibly be different for different plants in Europe. H2 might lead to higher thermal NO formation, but this can partially solved by existing combustion technology or adjusting the combustion technology. So this shouldn't be a big issue for the future. The demonstration of H2 combustion in furnaces is already happening, so as Joachim showed before, and it's also happening now in several European funded projects and also in other projects. These are more in national based. We already have some research needs that we have to do. We have to look closely on the processes and products and demonstrate the use of hydrogen in those furnaces on large scale to be sure that the processes work fine. What is missing at the moment is long-term experience, and we have to see if the burners will work for a long time, if the refractories work for a long time, and so on. Other issues are then standardization, so especially for the gas supply systems, for the instrumentation and so on, where there is some standardization missing at the moment. And the last point for the hydrogen combustion that is important is NOx emission legislation, because at the moment it is not a fair NOx emission values that are defined if we compare natural gas combustion to hydrogen combustion, because the humidity of the off gases is so different and it's calculated on a dry basis. Talking about ammonia, it might lead to higher fuel NO formation, and there possibly we will need secondary measures at our furnaces that we have not by now. Additionally, the low reactivity might cause issues reaching a complete combustion, but this could be solved if we add some hydrogen or partial cracking. An alternative could be the cracking of an ammonia to forming gas. And to sum up a bit, for ammonia combustion, we are much lower in TRL than for hydrogen. So for hydrogen, the demonstration in large scale is pending. They're working on that at the moment, but for ammonia, we have not seen it by now. Yes, that was my take on hydrogen and ammonia for downstream steel applications.
Thank you. Thank you, Nico, for your so well-structured talk on that topic and with a lot of information again here. Are there any questions to Nico on his presentation? This seems not the case. Then I would like really to thank you again for this presentation. It was really, really nice to see also the various concepts and where the furnaces are there and the solutions are there and where there is still some need for adaptations in the specific technologies. Thank you for that.
Yeah, thank you for the invitation. It was a pleasure.
Thank you. And with that, we are done for today. Even though we would love to stay together, the program is over. I would like to have a short round still of additional questions from your side. If there are some, if some has been popped up, we would have the opportunity still to do some sort of a short Slido, going back to the Slido at the beginning. So asking, what have you learned? Have you learned something new about industrial symbiosis in this workshop? So you are really welcome to type in some of your new additional insights that you gained during our presentations. I think it has been a really, really dense afternoon. So 8 presentations in 2 hours. It is quite a lot of information, and therefore we will try to collect all the content from the presentators towards also be able to publish your information, to have the option to read also afterwards something about it, and to come back to you in terms if there are additional questions and related questions. About transition, do we have something new about transition in the steel and chemical industry. It's pretty much comparable to the previous questions. So also here, please share your insights, share your new knowledge, what you think. And last but not least, what are your main takeaways from today for your work? I would say, speaking for the project, speaking for ourselves, there is a huge and abundant fruit for thought for this overall industrial symbiosis topic, and especially for the two sectors, iron and steel and ammonia production, where we put the landmark in new knowledge in here. So I think I'm totally happy for your presentations. A very, very big thanks also to the 8 presenters that we could engage on a very short notice. So really a big applause again for your commitment here. And that was really great. And well, if you have any other feedback you would like to share with us, please come back to us either by this Slido, we'll keep it open, or also directly by email. I really invite you to follow the project, also probably the speakers, the teams that you're working with. We still will come up with additional information, with additional deliverables that might be of a broader interest to all of you, for the whole community, for the whole, let's say, European industrial symbiosis community, more or less. And with that, I'm pretty much done. Thanks again for participating, for presenting. It was absolutely my pleasure, or our pleasure. And I will wish you really a very, very joyful upcoming Christmas season. And I guess we have a lot of new things to think about in the upcoming year 2023. That is my point, and that's it for today from our side. Thank you. Thanks to all of you.
Thank you. Bye-bye.
Thank you. Bye-bye.
And thanks you also,
Thank
Claire,
you.
to making us happening to come together for
No
that.
problem.
Thank
It was
you,
a pleasure.
Claire.
Thank you
Event.
so much.
Thank you.
Thanks
Have a
to
very
you.
good day.
Bye. Thank you, all
Bye-bye.
of you.
Bye-bye.
See you.
Bye bye.
Thank you.
Bye-bye.
Thank you.